Okay, so we're going to start our last lesson on stoichiometry, chapter 12, stoichiometry, lesson 3. So let me bring up my stuff real quick. Um, so we're going to talk about manipulating the equations just a little bit here. We're going to talk about what happens when you don't have the same amounts of each substances at the beginning. What happens, you're not always going to produce 100% in reactions, and so how to calculate what that percentage is that you actually produce, and so forth. So those are the two last little bits that we'll need to cover. Again, just using our multimole ratio. So again, here you're going to need your calculator, your notes and pencil for sure. So here is lesson 3. So our objectives here are using that multimole ratio to determine the amount of that's produced or the amount that will react given different amounts of reagents. So we're going to talk about whether or not, or if you have um, one reactant that is in a smaller amount than another reactant, then you're going to produce less of that substance or less of the product. And of course, you'll have something left over at the end, and we'll figure out how to determine what that excess amount of reagent is there as well. So using the limiting reagent to determine the amount of excess that remains of that other reactant. And then, of course, like I said, we'll do percent yield for a given reaction. Do a couple of them actually. Oh, wrong computer. Okay, so here, limiting reagent and the percent yield. So when you balance equations, when you use a balanced equation, it is that recipe, right? When you put all the stuff out on your counter to bake a cake or to the apple cake we talked about earlier, whatever that you're making, a lot of times you don't have exactly what you need, but you measure out what you need, you use that, and then you make your cake. At the end, you have stuff that's left over. That is what we call the excess. A limiting reagent would be one that you use up completely. And so when we do balanced equations, we'll set up to find out which one of those we're actually going to completely use. And if we didn't measure it out perfectly, maybe we have some that's left over. And that's why we were using things like excess reagent earlier. And so we've got a couple little examples to talk about here. So let's say you're making s'mores and you have 10 chocolate squares, 20 graham cracker squares, and 8 marshmallows. If each s'more requires a single chocolate square, 2 graham crackers, and 1 marshmallow, what is the limiting reagent here, right? So you need 2 graham cracker squares. I know this is silly, but just bear with me. So 2 graham cracker squares are what you need for each single chocolate square. If I look, I've got 10 chocolate squares at the beginning and 20 graham crackers. So I have the same amount of each of those. But I only need 1 marshmallow for each of these, and I have 8 marshmallows. So for each chocolate square, I need 1 marshmallow. I have 10 chocolate squares, but I only have 8 marshmallows. What is the limiting reagent? What's going to limit how many s'mores I can make? The answer is the marshmallows. I don't have enough of them. So I could calculate how many chocolate squares I would use with those 8 marshmallows, which would be 8. And I would have leftover chocolate squares, 2. I prefer the chocolate by itself. I'm not a big s'mores guy, so I would be excited that I'd have 2 extra chocolate squares. I would additionally have some extra graham crackers, but you get the idea. You could do the same thing with hamburgers, and I actually like hamburgers more than s'mores. But anyway, if you look at what we're given here at the top, those are the parts that a burger gets or they need. They need a top bun, a bottom bun, or a set of buns, a piece of cheese, a piece of lettuce, and the burger itself. If we look down here at the bottom, I'm looking for what is limiting how many burgers I can make. I've got 4 buns, I've got 8 pieces of cheese, I've got 3 pieces of lettuce, or 3 sets of lettuce, I guess, and 5 burgers. If you look at those, how many burgers could you make with 4 buns? You could make 4 burgers. With 6 pieces of cheese, I think I said 8, 6 pieces of cheese, you could make 6 burgers. With 3 sets of lettuce, you could make 3 burgers, and you could make 5 burgers with it. So if I just converted to how many burgers I could make with each, I could make 4 with this, I could make 6 with this, I could make 3 with this, and I could make 5 with these burgers. Not really, but that's how many I could make max. The thing that's going to limit how many perfect burgers I could make, granted, I could make them without lettuce, but the lettuce is going to dictate making the burgers the right way, right? That is the one that's limiting how much I can make. Now, I could have compared each to each and figured that out, but it's a whole lot easier to find out how much you would make at the end to determine which one is your limiting reagent and how much of what you're trying to produce you actually produce. So let's go do some examples. Chemistry examples, not burger examples. No more s'mores. Okay, so let's say I have 3.8 moles of hydrogen. They react with 2.2 moles of oxygen. The first thing I'm going to have to do is write my balanced equation. So my equation here is I am reacting, let's get the pen out, hydrogen with oxygen. And I could predict what that product is. It is water. And we did this as a demonstration in class, blew up a balloon and synthesized water from H2 and O2, same thing. I do need to go and balance this, so I'll put a 2 in front of here to balance my oxygens and a 2 in front of here to balance my hydrogens. I am given that I have 3.8 moles of hydrogen, and I am given that I start with 2.2 moles of oxygen. 22.2, tall it. 2.2 moles of oxygen. Okay, right away you're looking at it and you're going, oh, you have less oxygen. That oxygen limiting reagent. You can't do that. You need to use your mole to mole ratio to determine how much is limiting or is not limiting and so forth. The way we did it with the burgers is we found out how many burgers you would make, right? So if I went back up here, this dictated I could only make 3 and all the others I'd have stuff left over. So what I'm looking for here is how much of the product I produce. That's the easiest way to do this. You could certainly compare the amount of H2 to O2 and how much of one you need to make the other one, but sometimes it's just easier to find out how much you make. Done this a long time, this is best. So I need to find out what's limiting. So I'm going to take my 3.8 moles of H2 and I'm going to convert to the amount of water that I had. And I'm just going to do it in a mole-to-mole ratio. So I have 2 moles of hydrogen for every 2 moles of H2O. What I end up getting here is 3.8 moles of water is produced. Okay. I have another reactant or reagent. That reactant is the oxygen. I'm given 2.2 moles of O2. I need to go find out how many moles of water I'm going to make with that O2. Well, my coefficient for oxygen is 1. So 1 mole of O2 for every 2 moles of my H2O. And what I get here is 4.4 moles of water is what I could make. So it isn't whichever number is less. You've got to go find out how much you actually make from that because there are coefficients in your balanced equation. So the amount that I'm actually going to produce, and this is a question for later, by setting it up this way, you kind of solve extra problems. 3.8 moles of H2O is less than 4.4, which means that my hydrogen is my limiting reagent. So if it says, what is the limiting reagent? The limiting reagent here is the hydrogen. I realize that 3.8 moles is larger than 2.2, but this is relative to the balanced equation, not relative to how much you have. Okay. So that's part A. Part B, well, checking my answer for part A. Yay, look, hydrogen's a limiting reagent. It is because there's a lower amount of H2O produced. Okay, so if we go look at part B, how many moles of the excess are left over? So the actual excess was the oxygen. So what I'm going to do is I could do one of 2 ways. I could take the amount of water that was produced and find out how much oxygen made that amount of water. Or I could take my limiting reagent, which is what I'm going to do. I started with 3.8 moles of O2. And what I want to do is find out how much O2, let's say, how much O2 in moles I used. How much of it was it that I actually used up? And then I can subtract from the 2.2 I started with and see how much of it is actually left over. Now I'm going to scroll back up real quickly. If I went and I looked back at my hamburger example and I used those 3 pieces of lettuce, how much of the burgers would I have in excess? Yeah, I would use these 3. I would have 2 left over. So what we're going to do is we're going to take our limiting reagent, in this case it would be the lettuce, and find out how many burgers we use. What we're going to do here is take our limiting reagent of the hydrogen and find out how much oxygen we use. So I'm going to take my 3.8 moles of hydrogen and I'm going to convert 2 moles of oxygen. There are 2 moles of hydrogen from my balanced equation, 2 to 1. 1 mole of the O2. And what I end up getting here is that I actually used 1.9 moles of O2. That's what I used. That's what reacted with my limiting reagent. And so what I need to do now is subtract from my original amount. In the original equation, there was 2.2 moles of O2 that I began with, that I started with in my reaction, minus the 1.9 that I calculated that I used. And what I'm going to end up finding out is that I have excess, and that excess is 0.3. Oh, that zero's ugly. To the right of the decimal place, the dads, 0.3 moles of O2 are left over. So this is the amount of excess remaining. Now, these calculations are not always moles and moles. That we're showing you a pretty easy one here. You could go to grams and have to subtract from the original, but remember that the amount of that the limiting reagent is going to dictate how much is used of the excess reagent. It's also going to dictate how much water you actually produced. Let's check my work here. Yeah. Look there, 0.3 moles of O2 are left over. Sure. So this one here, it says how many moles of water were produced in the equation or in this reaction. Well, we kind of already did that at the beginning, right? How many moles of water produced? We solved for that in the first by just solving for how much water we produced. So we solved ourselves or saved ourselves from having to do that by doing that first one. So 3.8 moles of H2O was what was produced. Yeah? I used actually 3.8 moles of O2. It reacted with the 2.2 moles of oxygen, and I left some left over. How much I produced in that first reaction was 3.8 moles of H2O. What I want to do is convert this now to the second part of the equation where it says, how many grams of water did you have? Well, that's pretty straightforward. We just calculate our molar mass for water, which is 18.02 grams, and we can find out how much water was actually produced. The answer here to 2 sig figs is going to be 68 grams of water. So by solving for the limiting reagent, figuring out what it is, by solving for the amount that you produce, and then looking at which one produces less, we've actually solved part C, or half of part C already, which is convenient. And typically that happens. So if I go and I look at my answer here, yeah, 68 grams. The limiting reagent was H2. This is the limiting reagent, so that tells you how much of that you produce. And from the first part A, we got 3.8. So here it says how many grams of hydrogen can be produced when 4 grams of HCl is converted to 3 grams of magnesium. So this is a new problem. We're going to have to set up a new balanced equation. So it says that I'm adding HCl to magnesium. Ooh, that's getting big. So magnesium plus HCl is going to produce some products. Now, you guys should be able to predict products here. This is a single replacement reaction. So think if magnesium is above hydrogen on your activity series. It's a group 2 metal. It will replace hydrogen in acids. So I'm going to get my, my hydrogen by itself, and my other product would be magnesium chloride. Magnesium's charge is 2+, chloride is -1. So I'm going to get MgCl2, and I'm going to be left with hydrogen. Hydrogen, of course, is diatomic, so I'll write my 2. I need to balance this equation with the 2 in front of the hydrochloric acid. And then I'm going to go and set up my problem here. So my given and my wants, I am given that I have 3 grams, 3.00 grams of magnesium and 4.00 grams of the hydrochloric acid. It says how many grams of hydrogen can be produced. So what I'm looking for is my hydrogen, and I want it in grams. But I have 2 different reactants that I'm given. I need to find which of those is going to be my limiting reagent. I don't know that. And so what I've got to do is go and solve for the amount of hydrogen that is produced from the magnesium and the amount of hydrogen that is produced from the hydrochloric acid. So I'm going to set this up and then turn you loose to go try it on your own. But you start with your 3.00 grams of magnesium and change that to hydrogen, whoop, as one equation. And then you're going to take your 3.00 grams of hydrochloric acid and change that as well here, whoop, to hydrogen gas as well. and see which one produces less. So why don't you hit pause, go ahead and do it. It's just two mass calculations. You'll need the molar mass of magnesium and hydrochloric acid as well as hydrogen. Okay, give it a shot. Okay, so I'm gonna brush through this kind of quickly since you've already checked your work, just looking to see if it's the same. So 24.31 grams of magnesium off the periodic table is 1 mole of magnesium. My mole to mole ratio from start to finish here is 1 mole of magnesium is 1 mole of hydrogen gas. And it asks for how many grams of hydrogen, so I'll need a molar mass of hydrogen. 1 mole of H2 is 2.02 grams of H2. Then I'll go solve for my answer. I got 0.249 grams of H2. Now I'm going to go take my HCl. So my hydrochloric acid molar mass is going to be 36.46 grams of HCl is 1 mole. I have a 2 mole of HCl to 1 mole of hydrogen mole ratio. And then once again, my molar mass, kind of convenient that they work out this way, but I'm looking for the grams of hydrogen, so I'll use my same molar mass I already calculated, which is easy. Hydrogen, and in this case, I get 0.111 grams of hydrogen. Which of those two is less? Here. That is how much that I'm going to make. What if another question said, what is the limiting reagent? The limiting reagent, the one that actually produced that, is going to be my HCl. So if I had other questions that are being asked about this, I'm going to use my 3 grams of HCl to go figure out, say, what's excess, or I guess that would kind of be the only one, or how much magnesium reacted with it, suppose. Yeah, that would be good. Let's check my work. Well, there you go. And HCl, did they ask what was limiting? They didn't even ask what was limiting, but HCl is your limiting reagent. So for part B, it says, assuming at STP, what is this volume of hydrogen that's produced? Okay, I could start with my limiting reagent and change it to I could start with HCl and I could change to hydrogen and go from grams to liters. I could just use the mass of the hydrogen that I have solved for that's going to actually be produced and convert that to liters, which is what I'm going to do. But it doesn't matter. There's a couple different ways to do this. I would take my real answer, though, from the other one without rounding, the 0.111. It may not make a difference, but it might. I would use my entire answer out of my calculator for this. And I'm going to change the grams of hydrogen to moles, 2.02 grams. H2 is 1 mole of hydrogen gas. And then 1 mole, of course, of hydrogen gas is 22.4 liters of hydrogen gas. And I go get my answer. For this one, it's 1.23 liters of H2 that's produced. So that's just kind of a little stuck on thing there at the end. You could have certainly used your HCl as your starting point instead of your hydrogen. We just chose to use the hydrogen. If you're going to do that, though, like I said, make sure you use your entire calculated amount of hydrogen in your calculator rather than rounding to 3 sig figs and then doing this problem. Okay. Let's check my work here. Boom. So that's limiting reagent. Sometimes you're also asked, how much did you make in reality? So this will be our theoretical and our actual yields. So the theoretical yield is what you get by calculating, right? So if you put all your ingredients together for your cake, you should get a certain mass of cake at the end. We all know you never really get the same amount. It's a little bit different. Some of it's going to be stuck on the pie pan or the cake pan, and some of it will boil over, bubble over in your oven if I'm cooking it. You know, there'll be mistakes, and so your yields are not really going to be 100%. Some of you get yields that are greater than 100%. That's not good. They should be less than 100% or 100%. Hopefully you're not creating mass. That's not a thing. But your theoretical yield is observed when your equation is used to calculate. So you use your balanced equation to find out the amount you should get as a result. That's your theoretical yield. The actual yield is what you get in the experiment. So this is your experimental value, and then your calculated value is your theoretical. Theoretical is always calculated, and your actual, they're going to have to tell you, or you perform the experiment yourself, and it's It's what your result is. And we'll actually do a lab where we do a little bit of this. So let's go look at the percent yield. So here's your calculation. Your actual yield should be less than your theoretical yield. And so you'll get a number that's less than 100%. But not always. You may have done something wrong. There may have been gases in the atmosphere that bonded to your product, and so the actual mass is larger. Or you could have made mistakes. Yeah, maybe you didn't zero your balance. Oopsie. So yeah, it'll be the actual yield divided by the theoretical yield times 100. Remember that your theoretical is your calculated, and your actual is either going to be told to you, which it would be on an exam, or I could give you experimental data and you would have to use that as your actual yield. So let's go try an example. So what is the percent yield if 3.74 grams of copper is produced when 1.87 grams of aluminum is reacted with excess copper 2 sulfate? Okay, good. We're not given two reactants here. We're only given one, and we're told the other's in excess. So we don't have to do a limiting reagent problem here, which is a good thing. So let's go try. So we've got, oh, what am I doing? I'm missing my business here. So I need to write a balanced equation first. So aluminum is going to react with copper 2 sulfate. Sulfate is a 2- charge, copper 2 is 2+, so this is going to be CuSO4. And I'm going to produce aluminum sulfate, which is going to be Al2SO4 3. Aluminum is above copper on the activity series. It is more active, so it will replace the copper. And what I'll be left with as another product is copper. I need to go balance this thing. Let's see, I've got 3 sulfates there. So let's go put a 3 in front of the copper 2 sulfate. That changes my number of coppers. And I need 2 aluminums to balance my aluminums. And there we go. I'm told I have 1.87 grams of aluminum. And I'm told I have excess of the CuSO4. So I don't even need to worry about the CuSO4, the copper 2 sulfate. What I'm looking for is, let's see, what is the percent yield of copper? So I'm looking for the grams of the copper that are produced. So I'm going to start with my 1.87. Now, they're telling me a number in here of copper. That right there is your actual yield. So that's what they did in the experiment and got as a result. We're going to go calculate what we should have gotten as a result. So if I start with my 1.87 grams of aluminum, I'm going to do a conversion to find out how much copper should have been produced, my theoretical yield. The atomic mass of copper off the periodic table is 26.98 grams. Oh, sorry, of aluminum. 1 mole of aluminum is that 26.98. I can do a mole-to-mole ratio. There are moles of aluminum. I am transferring to find the amount of copper. So moles of copper is a 2-to-3 ratio for my balanced equation. And then 1 mole of copper has a mass of 63.55. What I end up getting as a result here is 6.61 grams of copper. This is what I should have gotten. This is my theoretical yield. So my percent yield calculation is going to be my actual divided by my theoretical times 100. Yeah. So my actual was what was given in the problem up at the top. It was 3.74 grams. So I'm going to take my 3.74 grams. I'm going to divide that by 6.61 grams. And don't forget to multiply by 100. We want a percent, not a decimal. So what we end up getting is 56.6% as our yield, which is actually kind of low. It's kind of low, but it's okay. I mean, it's reality. Reality is you can get some low percent yields. That's okay. Could even be lower than that, I suppose. But that's calculating. You calculate your theoretical yield, what you should get as a result, and then you're always given your actual yield. Unless, of course, they give you the percent yield like they do in the next problem. So let's go through the last one and finish it up. Checking my work. Yeah, it's 56.6% yield. They took up far less space than I did. Look at that. That's just a mess. Okay. So here, the percent yield is actually given in this problem, and we're given the percent. So we're given our percent, and we're given our starting point. So we don't know what our actual yield is. So what we're saying is what mass is expected. So what they're looking for here is what is our actual yield when we get an 83.2% yield. So what we'll have to do is go solve for our theoretical yield and then do just a little bit of algebra. So here we're starting with 73.7 grams of PCl3. We're told we have excess chlorine, so we don't need to worry about that. And what we need to go find is the grams of the PCl5. So here what we're looking for is this mass. This right here will give us our theoretical yield. Yeah, how much we should get from the calculation. So why don't you guys try this one? There's a little bit of algebra at the end. I think you'll be okay. Just pay attention to your formula, plug it back in to solve for your actual yield. Give it a shot and I'll come back and show you how to do it. Okay, so I'm setting this up to go solve for my theoretical yield, 73.7 grams. I'll need the molar mass of phosphorus trichloride, which is 137.32 grams PCl3. That'd be 1 mole. And it is a 1-to-1 ratio. It's balanced, right? Yeah, it's balanced. 1 mole of PCl3 is 1 mole of my product, which is PCl5. And 1 mole of phosphorus pentachloride is a whopping 208.22 grams. And so my theoretical yield here, how much I should have gotten, is 112 grams. Now we're looking for our actual yield. So writing my formula here, my percent yield formula is my actual over my theoretical times 100. Well, this case, I know my percent yield is 83.2. My theoretical yield I calculated is 112 grams, and my actual is what I am solving for, times 100. So we'll do a little algebra here, and what you end up getting for your actual yield is 93.0 grams of PCl5. So we didn't get the 112. The 112 is what we should have gotten. In this particular experiment, they're only getting about 83.2% of it. So how much did they actually get, or did we actually get, is 93 grams of PCl5. That's kind of the ways that you'll see this. Generally speaking, remember, you always solve for your theoretical yield by doing a calculation. Your actual yield, you will either be given it or you'll be given your percent and you go solve for your actual yield. Let's go check my work. Much cleaner than what I had there. So that was it. That's the end of lesson 3 for you guys. It's the end of stoichiometry. We're gonna have a couple of practice before we take our exam. I'm not sure as far as I think we haven't done the lab yet, but we'll do a lab as well with a single replacement reaction that you guys will see. That's a good lab. And there you go. Oh, look, chemistry is still fun. Okay. Thanks guys for watching me. Maybe you'll get to see the Aiken again next time.